All right. Okay, so here's just a random search, not really random, just a search for direct variation problems. This is kind of where K comes from. So if you remember problems like this from way back in the day, if Y varies directly as X, or with X, probably what I would say, and X equals 9 and Y equals 15, find Y when X equals 33. So if you remember how to go back and solve these problems here, one of the things that you do is say, okay, well, varies directly means I have this relationship Y equals K times something. And that K is just like representing however much this constant is. And so example I give the students in class is like if you get paid per hour. You don't get paid $1 for 1 hour, that'd be horrible. You get paid however much money per hour. And that's basically what that K represents, is what's the rate that you're working with here. So for this problem, we'd set this up as just direct variation. They tell us some information about Y and X, so let's go back and solve for K so we can go back and plug it in. But in the problems that we're doing here, we don't have quite that much information there. So it's still a similar idea. We're saying that it varies with something. It's proportional to something here. And so we don't know what the rate is, but that's what that K represents, is basically what rate is this thing proportional. We don't know that, so we just put some constant in there to kind of absorb it. And yeah, we're never going to go back and solve these for K. That's kind of the same idea. It's like whatever rate we're talking about being proportional with.
So how can we do an example 2 here, but not an example 1? Is it because it's not the same thing about proportionality?
So in example 1, they told us what the density was. They said, this is your density function. They said it is 2x plus y. Okay. Basically, the rate isn't 2, but in the x direction, the rate was 2, so like they told us what it was. Whereas in the other examples, they'd said, okay, well, you know your density is proportional to the distance, but we're not going to tell you what the equation is. And so in cases where they don't give you the equation for density, they tell you something like this, you're going to have to use the K. And equations where they tell you what density is, you just use the equation and tell you. That's just it.
Thank you, that makes sense.
Good. All right, so we finished up this problem. We're okay with question or example 3. I think we had plenty of time to talk about it. Yeah. So then we left off with moments of inertia. And there's those equations. We're not going to go through, try to reason them. You can kind of draw parallels between these and other ones here. I was trying to, because I'm not going to lie, inertia to me, yes, it makes sense, but it's like once I have to explain it, it's a little more difficult. But I did find a website that said something I liked a lot. It said that, like how mass measures resistance to change in a linear direction, inertia is measuring resistance to change in a rotational direction there. So it's kind of a similar measure to what mass would do, but in a different direction, essentially. So even without that, there's the equations that we have for inertia. You can kind of think about it as taking some region and rotating it about something. And depending on what that something you're rotating about is, that's going to change your equation. So the inertia of x, this is saying basically about the x-axis. And we're not going to worry about moving this to vertical lines or horizontal lines. We're just going to keep on axes. Okay, that's something for a physics class to deal with. I sub y is the inertia about the y-axis. And then the I sub O is the moment about the polar axis. You can kind of think about rotating about the z-axis, kind of what that comes down to. But it's technically about the origin, the polar origin. It's kind of like thinking about the z-axis. So if you imagine taking some solid and rotating this, where you know the density of this solid here, that's what these are describing. For us, I've got 2 examples in there. We won't go through all the math for them. I didn't really leave enough room to go through all the steps, so we'll skip a little bit here. But the important thing, like last time, is just really the setup. I mean, if you can't get these things set up correctly, it doesn't matter how good you are at solving them. So make sure we can get the setup there. So example 4. Find the moment of inertia about the x-axis of a lamina corresponding to the parabolic region. This, where the density at a point is proportional to the distance from the x-axis. So like George is asking about, we're not told an equation for density. This is going to be a problem where we go back and use K. Since we're doing moment of inertia about the x-axis, it'll be that first formula on the previous page there. So we need to define what the region is, decide if we're going to use polar coordinates or rectangular coordinates, and also figure out a formula for our density there. Let's start with that region. And like Stephanie said, yes, I do suggest graphing this basically every time. All right, moment of inertia about x-axis, lamina corresponding to the parabolic region. 0 is less than y is less than 4 minus x squared. So if we graph this guy, it's a parabola. It's been shifted up 4 units and reflected. Less than that and greater than 0. So we're just talking about that little space between the x-axis and that parabola. So that's the region for this one. Should we keep it rectangular or switch to polar? Yeah, unless it's a circle, I wouldn't even try to worry about switching. Okay, there's very, very few cases where if it's not a circle, it's easier to switch. So don't worry about this. Okay, I won't expect you to come up with that. So keep in rectangular coordinates, which means now we need a formula for our density in terms of x and y. And we are told that density is proportional to distance from the x-axis. And this is very similar to the one that we did yesterday. So this is still going to be just k times y. We get the distance from the x-axis. It's the job of y. Y tells us that. So here we go. If you want to make your picture a little better, like we said last time too, this is more dense towards the top. I don't know if that really helps any, but more dense towards the top of this. As we get further away, it gets more dense. All right, now to put it all together. Inertia about the x-axis. We said we'll leave our region in terms of r, or I'm sorry, in terms of x and y. So we'll cover those in a minute. On the previous page, it says about the x-axis, we are going to have y squared times our density function, so times ky. And then should we do this dy dx or dx dy?
Dy dx doesn't matter. Yeah.
Yeah, dy dx does work out nicer. If we did dx dy first, we'd be looking for the change in our horizontal direction, so we have to go back and resolve our parabola. And it's doable, but this is a little simpler. So what would be our limits of integration for y?
Y was 0 to curve.
So 0 on the bottom, and then our function on top. So 4 minus x squared. And what would be our limits of integration for x?
2.
Yep. This is the same region in the last example, so if you want to go back and look at the last example or rethink it that way, it's the same region. Really the only difference is talk about inertia instead of centroid, so we have a y squared there, so just y. So that the reason this one kind of gets messy is, yeah, it's just the power rule, but we'll do the first part and then kind of see where it gets a bit sloppy. I didn't really leave enough room to work this. We'll just multiply something to the fourth, which is just a lot of work. So outer limits stay the same for now. This inside is the same thing as k times y cubed. K is just constant. If you want to put all the way out front, that's fine. And in fact, let's go ahead and do that. One less thing to have to worry about as we work throughout here. And so if we have y cubed, what's the antiderivative of y cubed with respect to y?
Why do we have y squared?
Because that's just what the moment of inertia said, and I didn't go through and reason through the formula. On the previous page, it says inertia about x-axis.
That's right.
Evaluated from 0 to 4 minus x squared. And that's where it starts to get messy. If we take 4 minus x squared and multiply to the fourth, it's just a real big polynomial. So that's just a lot of practice in doing algebra here. However, your calculators can do this stuff. If you got the fancy 89s and 92s, it'll go ahead and do that out for you. So it's not too much work with a calculator. But doing it by hand, it just takes a bit of time there. Actually, I'm going to pull that 1/4 out too. That's this k over 4. One less thing to worry about then also. And then minus 0. And that's just where, like I said, from here, it's just a lot of algebra. But you could go through and do it. It is just algebra. Nothing's really tricky there. Just be careful keeping things in the right spots. Eventually, you're going to go back and substitute in the -2 and 2 to find the antiderivative. So we're going to do a bunch of algebra. And then I'm also going to know a bunch of Calc 1 stuff. Eventually, we will get really nice number, 32,768 K all over 315.
Yeah, these are those answers that you just don't believe.
Yep. Yep.
So there's no rule for that, the integration of that.
So we have the integration tables we talked about in Calc 2. It's possible the integration tables might, but I don't think they really do. I think this is just like multiplying out your polynomials. So yeah, you'll multiply them out, use product rule a whole bunch, or distribute a whole bunch of times, and then use power rule. Yeah.
Did you calculate multiply?
Yeah, the calculator is multiplied out. If you use the fancy calculators.
I know that you could just put that in for the integral and solve.
You can do that too.
There's a good online one that is pretty good too.
Do you have to remember the name of it?
I just put angle calculator and pulled it up.
Oh, there are tons of things online. Yeah, if you guys are smart about it. Which one?
Mathway.
Mathway, yeah. And I know Wolfram, you have to pay to see the steps, but Wolfram is another good one.
It shows stuff pretty good, so.
Yeah, and I mean, I know that it's very easy to cheat. I trust that my students, especially at the higher levels, are using those things responsibly. But if you use those things responsibly, I mean, there's a lot of really awesome resources out there. I'm not gonna lie, I do stuff too. If I get stumped and I can't figure it out, I ask the internet for answers also. I mean, kind of silly not to. But yeah, as far as even just expanding that thing out, I'm not positive you have to tell it to expand. Yeah, so if you go to F2 algebra, there's expand, that third option there. And I don't use this often enough to know for sure if this is the right notation. We'll find out. Yeah, and you just expand, enter the polynomial, which I typed wrong. I typed my polynomial wrong. But if you type in the right polynomial, it should tell you the answer. So you can scroll through that to get the rest of it. Okay, this isn't right. I put the wrong thing in there. So
sometimes it's hard knowing what like the format is.
I mean, the calculators do a lot of stuff, but yeah, I don't know. I do a lot of it by hand. And even as a student, I did too. Sorry. Those of you that like your calculator, just apologize. But yes, even like you said, you can take your original integral and plug it into your calculator to make sure it's the right thing too. And the good thing about these calculators is it'll give you exact answers. So you don't have to worry about approximating, which is the problem with 84s. Okay. All right, so skipped a lot of step there, but the setup. All right, another one, let's get this guy set up and we'll do a similar thing. We'll talk about how to solve it and then we'll see if, and I haven't checked the answer for this one yet, but I'm pretty confident. Find the moment of inertia about the x-axis of the lamina corresponding to, it is not a parabolic region. I copied and pasted too much, so you can cross that word out. Corresponding to the region x squared plus y squared equals 9 in quadrant 2, where the density at a point is proportional to the distance from the line y equals 3. So changing a few things, changing up the shape. We're in quadrant 2 just to do something different. We're always in quadrant 1. And then our proportionality function is going to change a bit too. But like last time, let's start off by just thinking about the region we're working with. Okay, no matter what problems we're doing in this chapter, it's probably good to start off by thinking about that region. And if we ignore that word parabolic because it's wrong, and then think about the region, what shape region are we working with?
Circle.
Circle. Okay, what a radius of?
3.
Radio. And since we are just in quadrant 2, we are just going to talk about this portion of the circle over here. And again, just for something different. We are also told moment about the x-axis, so kind of think about spinning this guy. We're trying to measure its resistance to that spin, where the density is proportional to the distance from the line y equals 3, which is also a little different than what we did before. So the line y equals 3 is this horizontal line up here. So how can we use that to write our density function?
So it's from the origin of the line. You want to go down, so it'd be negative y plus 3.
You could do it that way for sure.
Okay. Almost okay.
Yep. If you don't like adding negatives, you can write it as 3 minus y, and that would be all right also. Think back to the days where you loved doing surfaces of rotation or solid rotation, having to rotate by like a vertical horizontal line. You have to shift your radius or shift things like that. It's a similar idea there. If we're talking about from y equals 3, and it's the further from that line, the more dense it is. When we're at y equals 3, the density is essentially 0. And as we get smaller values for y, the density is going to increase there. And so you can go back and try some formulas, but that would be a function for this. Polar coordinates, or leave it as rectangular.
Polar.
Why polar? You could leave it rectangular, and it is doable that way. It's just going to be a lot more work. So yeah, I think polar coordinates are definitely going to be easier because the shape of this region. So I'll note that since R is circular, let's use polar coordinates. All right, so set up inertia about the x-axis. Actually, before I set that up, let's be a little more clear since I wasn't clear enough before. We're going to need to rewrite our density function in terms of polar coordinates. So how can I do that? How can I take this density function we have and write it in terms of polar coordinates?
Change the y.
So we still have k, we still have 3, but now y is going to be r sine theta. And how can I describe that region of integration in polar coordinates? What is r going to range from?
Pi over 2 to pi.
Okay, so theta will go from pi over 2 to pi.
Oh,
Yep.
yeah,
And then r will go from 0 to
3.
No, you're fine. You just got the tricky part out of the way. All right, so inertia at the x-axis, again, on the bottom of the previous page, kind of gives us a format for this. I'll leave a little space, we'll look back to that in a minute. We are going to have y squared, but we can't leave it as y, so we're going to have to write this as r sine theta squared. Okay, again, usually it should be y squared, but we're converting to polar coordinates, so we have to convert that part too. And then times our density, which we already converted. Then times r, since we're doing the conversion to polar coordinates, and we'll stick with dr d theta. Limits of integration, we said for r from 0 to 3, and for theta from pi over 2 to pi, since we're in quadrant 2. And I'm now less confident because I told you guys I always forget to put r in my notes. So my answer in my notes is wrong. So we'll have to use a calculator, which is, seriously, I do that all the time. I have it highlighted so many places in my notes, but I forget to go back and do it. I'm surprised it's the first time I've done it here. From here, we'll get it started. We can simplify this a little bit. So pi over 2 to pi stays there for a bit. I'm going to leave the 0 to 3 there for a minute too. What would we do to this integrand? If we're going to do this whole thing by hand, what would you do to that integrand?
Plot the k.
Plot the k for sure. Let's go ahead and do that.
Distribute.
Yeah, and so make sure you're squaring both the terms in the first guy and then distributing that r to, well, a whole bunch of distributing happening here. So we'll have r cubed in total times sine squared theta times 3 minus sine that guy. So taking that r and this guy and combining those to give this term. And then yes, go through and distribute.
Again.
So k, all my integration is still there. Haven't done any integration yet. And what do we have? 3r cubed sine squared theta minus r to the 4th sine.
Should the r to the 3.
Well, I put the r just right here first.
Well, no, in your second equation, now the r is to distribute. So you got 3 minus r sine theta. You got to distribute r to the 3. That's it. Oh, no.
Yeah, I see what you're saying. So if I would have distributed it here, yes. Yeah. Yeah, okay.
That's right.
What do I need here? Cube theta. Okay, and I am going to stop here because from here it's just getting more complicated. If we're going to finish doing this by hand, and again, I'm not going to ask you guys to go through stuff from Calc 2 by hand in this class, but if you were going to go through and do this by hand, this is a lot like stuff you did in Calc 2. There's like a whole section in Calc 2 where we talk about trig integrals, and if we have sine squared, well, that's not too bad to deal with. Sine squared, we've got identity before, we can use power reducing identity, write that in terms of cosine, so we can deal with that one. But when we get to the point where we're trying to integrate the sine cubed of theta, that's going to be one where we have to go back and rework it and use substitution. And it's not impossible, but it takes more work than I want to do right now in class here. So first, integrate all respect to r, which that part's not difficult because then the thetas are all just constants there. Go back and do some substitution, have more constants, but once you get past that, integrate with respect to theta takes a little more time here. Like I said, I goofed, so what I have in my notes is not correct. So let's see how the calculator handles this. Yeah, it does feel like cheating. Okay, so antiderivative of the antiderivative of 3 times, there's no easy way to get r. And I typed it 2, which doesn't even help.
How did you get the density equation for like the very beginning? Just for this problem? Yeah. So how do we do it from the line up? So don't even think about quarters, because there are quarters to that, think about quarters. But you know how we do it from like the line up, it's just y. Yeah. Well, we want to go, first we want to go down. So you go 3 down, so negative y. Right, so we might line up 3. Okay. Yeah, I guess that. Motion. Okay, yeah, I see.
Shoot, there's a lot of stuff typing. I'm sure I made a mistake somewhere.
That's what started on the calculator.
Okay, so let's see what happens.
One type.
All right, let's first check this. Okay, pi over 2 to 2, or pi, that's good. 0 to 3, that's okay. 3 r cubed sine squared. R to the 4th. And I use t instead of theta. Sine cubed. Oh, well, I think I entered it correctly there. So there's the exact answer. And just thinking for an approximate answer. There you go. 0.16 should be the approximate answer if I type that all in correctly there. Sorry.
K, right?
Yes, times k. I left the k out too. So k times 0.16 is the approximate answer here.
Sure.
Problems like this for tests, I'm just going to ask for a setup on. Okay, I'm not going to ask you to go through more with this. I know not everyone has a fancy calculator, so I'm not going to ask you to bother going through and try to type that into 84 or something like that. This would be a problem where I say, okay, well, sketch the region, set it up, polar coordinates for counter coordinates, but I'm not going to make you go through and do math on these. There's plenty of simpler things where I can see if you can go through this process. Okay, so sorry for picking a bad one and not having the right answer there, but hopefully the setup kind of makes sense. And if I did make a mistake somewhere, I'll remember to go back and check later. I'll point it out, but I think we should be okay. All righty. There we go. 14.4 questions.
That's fine.
Well, starting a new section with 5 minutes is awkward, so we'll quit here. So we'll do this next time. I'd rather not get 5 minutes into the new section. We'll just wait and do it tomorrow. Okay. So if you got questions, let me know. Homework for this should be posted. Yeah, I think I have it all taken care of now with homework that should be posted. And if you have questions to work on, just let me know if you guys are good. Oh, if there's problems with the test, let me know about that too. If I graded something wrong, or when I do get them typed up, just make sure I typed it up correctly. Just let me know if you guys find issues.
Is the homework on 14.5?
The homework that is coming up this week is 14.4, 5, and 6.
Okay.
So, a bunch of stuff.
I probably missed this. So when you say and y is
Solve numbers except for the okay. So if you have, like, say x is -1 and y is 5, is this going to work? Right, because you can have negative radicals. So that's why you have to make sure the product is something positive.
That's right. Yeah.
And you're not the only one. There's a people that kind of thought about that a little awkward there. But yeah.
Because I was like, how does it have points in my body? Yeah. Oh.
All right. Edwin, I wasn't able to hear you guys. I don't know if you had questions. I did end up saving it. Were you able to see things and hear things okay? Yeah, okay, all right. Hopefully we can get that mic thing figured out. Let me know if I can help at all, okay? Okay, bye guys.
Sign language.
For